My name is Dave Heimann. I'm a hydrologist with the U.S. Geological Survey. I work out of the Lee Summit office. Our primary office is in Rolla for the Missouri Water Science Center, and the center has two primary functions. One is the basic hydrologic data collection, and that includes stream flow. It includes water quality of both surface and groundwater resources, and it also includes groundwater monitoring. The second function that we do is studies or projects, and these are in cooperation with the state, federal, local agency to address or answer a specific question or problem. And tonight's talk, Where's the Mud? Understanding Sediment, Sources and Storage of Sediment in the Big Muddy, utilizes some of the information gained from both the projects and the data collection side. This, by the way, is the confluence of the Big Muddy with Mississippi. So sediment and the river we now call Missouri have been synonymous for some time. The native peoples recognized it as being different and in terms of its sediment load. And they had various terms that are translated to various sediment terms, including those of the Algonquin that called it River Paquitanui, meaning muddy it flows, and the Dakota Sioux had various terms referring to smoky water or muddy water or stirred up. And the Hidatsis referred to it as a wati, or navigable stream full of dirt. The Europeans had their nicknames for it as well, including the Yellow River, the Muddy Mo, and of course the Big Muddy. The Yellow River, that one I was confused with initially, but I did a little digging. And my understanding is that when the river historically had high flows and the sediments were all stirred up, it would have a yellow tinge or a yellow color. And that was because of the highly weathered clays from the Dakotas that are yellow in color, and they would color the river yellow. But all those clays are behind impoundments now, so we don't see the Yellow River anymore down here. I wanted to provide a little background information, including some terminology. What I'll be talking about primarily this evening is suspended sediment. That's the component of the total sediment load that's in suspension primarily in transport, versus the bed load, which tracks near or at the bottom during transport. The suspended sediment load is generally thought to be about 90% of the total load, whereas bed load's about 10%, but that can vary. There have been some bed load measurements of the Missouri River that were upwards of 30% of the total load. A couple of terms I want to mention are suspended sediment concentration, which is the mass per unit volume, and we measure that in milligrams per liter. Also load or mass flux. So the sediment load is the concentration times the total flow, and that's the mass per unit time, and that's measured in tons per day, or metric tons per day. So I was curious how the Missouri River stacked up to other rivers in the world in terms of total sediment transport. In terms of load, the Amazon comes in at number one at about 1,320 million tons per year on average, and the Missouri came in at number 8 at about 310 tons per year on average. But that was using the historic values. The current values are in parentheses there at about 66 million tons per year. In terms of the yield, which is the total load divided by the drainage area, the copper comes in at number 1, that's in Alaska, and the Missouri came in at number 11. But that again is using the historical loads. This is a concept that I wanted to introduce. It's Lane's balance or Lane's principle. And what this states is that the driving forces in a natural stream system, the driving forces which include stream flow and stream slope or stream power, are in proportion to the resistant forces, which are sediment load and the sediment size. And so I'll provide an example of that. So we'll use the Oroville Dam near disaster as back in February as an example. So we start off with heavy precip. which causes the impoundment to fill and spill over the spillway. And then that results in, on this side of the balance, with an increase in stream flow, we have an increase or a tipping of the balance downward, and that results in a degradation condition. And then the spillway initially resists that extra flow, but when it starts to, bit by bit, it starts to break up, and then it wants to come back into equilibrium, and so it starts picking up sediment anywhere it can get it. It takes out the spillway and then takes out the hill slope as well. But then there's another condition that takes place because the spillway empties out into a low gradient main channel, and so there's a change in the slope, and that results in a degradation condition because we've lost stream power, and then the sediment load drops out, and you can see the deposition that occurred as a result of that. So I'll be talking about a streams balanced sediment regime later on, so I wanted to introduce that. So the primary topics that I'll be presenting there will be 4 topics, and it'll include the historical perspective of sediment measurements and alterations on the Missouri, the current sampling that's being conducted by the U.S. Geological Survey in terms of sediment monitoring on the Missouri, a general sediment budget. This is a study that I recently completed, and then this idea of a natural sediment regime. So what I'll start with is a kind of a timeline of some historical measurements that were made on the Missouri River beginning in 1804 with Lewis and Clark. So Clark states in June of 1804 that the water that we drink contains half a common wine glass of ooze or mud to every pint. And then Lewis states that same year in 1804 that the precipitate of 1 pint of Missouri River water weighs 80.65 grains. So we can take that information and then we can convert it into the modern units and into milligrams per liter, and I'll do that in a bit here. In 1843, as part of the Audubon expedition, Edward Harris collected a sample in May of 1843 near what is present-day Gavin's Point Dam. And he states that the water looks more like a hog puddle than anything else I can compare it to. About 1/10 of its bulk forms a deposit in half an hour. Then in 1879, the U.S. Army Corps of Engineers collected the first daily samples on the Missouri River, and that was near St. Charles, Missouri. Then in 1900, the city of St. Louis and the state of Missouri collected samples on the Missouri and on the Mississippi, including sediment samples. And this was part of a lawsuit between the state of Missouri and the state of Illinois and the city of Chicago. And Missouri and St. Louis claimed that Chicago was dumping their sewage into the River des Peres, which flowed into the Illinois River, which flowed into the Mississippi River just upstream of St. Louis. So this went all the way to the Supreme Court, and the judge ruled against the state of Missouri, stating that that's a pretty far distance and they should look near or close to home for the source of the pollutant rather than blame Chicago. In 1907, the USGS collected some 10-day composite samples at Omaha and St. Charles. And then in 1929 to 32, there was a more extensive study by the U.S. Army Corps of Engineers to look at sediment concentrations and loads at 8 stations along the Missouri River. And then this is when I consider the sampling program to really have begun, which is in 1936. And that was conducted by the U.S. Army Corps of Engineers, and they collected samples at 7 Missouri River stations and numerous tributaries as well, and they calculated daily loads, monthly loads, annual loads at all of these stations. And then the USGS took over that program in 1976, and we continue that program. I show pictures of flooding here because that's an important component in terms of not only of the water, but the sediment as well, as most of the sediment for the year is likely to be transported during that one single event. So here's that compilation of some of those historical measurements with the modern day measurements in terms of the instantaneous sediment concentrations. The concentrations vary anywhere from about 10,000, and this is that hog puddle sample, that 160,000 milligrams per liter, which is an incredible number. I'm thinking that Edward Harris probably collected that sample just downstream of a bank failure or something to get a value that high. But that value is in direct comparison with this 42 milligrams per liter. That's the Yankton, South Dakota maximum sediment concentration between 2000 and 2009. So those two concentrations are at basically the same location. And this shows the comparison of those composites or multi-day samples compared to averages from modern day. And we have, again, a disparity where we have a range of about 1,600 to 4,100 milligrams per liter, and present-day concentrations average more along the lines of 600 to 700 milligrams per liter. So now I'll go through a timeline of some of the activities that have affected sediment transport on the Missouri River as well. And that includes, in the period 1838 to 1929, there were just site-specific bank stabilization or dredging projects that didn't have any far-reaching effects on the sediment. And then in 1930 to 1936 was one of the first more systemic alterations with the construction of the 6-foot by 200-foot wide navigation channel and bank stabilization as well. Then in 1937 was the first of the main stem impoundments, and it was Fort Peck Dam that was constructed in Montana. And then between 1950 and 1962, they expanded that 6-foot by 200-foot navigation channel to a 9-foot deep by 300-foot wide navigation channel. Then in 1952 to 63 was the completion of 5 more additional main stem impoundments on the Missouri. And in addition to the impoundments that were constructed on the Missouri, there were several that were constructed on the tributaries as well, as 1951 and 52 were both high flood events. So for instance, on the Kansas, there were several impoundments that were constructed during this period as well. Then between 1930 and 1981 was the Corps of Engineers Bank Stabilization and Navigation Project. And what this did was to take about 800 square miles of active channel and convert it into floodplain, basically. They put up the structures, trapped the sediments, and resulted in the buildup of additional floodplain and the loss of that active channel. Then between 1935 and the present, there's been dredging activity, commercial dredging activity that's affected sediment to some degree. And then from 1995 through present is the construction of emergent and shallow water habitat on the Missouri by the Corps of Engineers. And this was done in order to mitigate some of those effects of the impoundments as well as the bank stabilization project. So what this has done is taken a wide, meandering, multi-channel system and converted it to a narrow, armored, self-scouring, more well-behaved channel that's more conducive to navigation. So in answering the question of where's the mud, there are a number of factors, and it's not limited to the alterations affecting the sediment side of that balance, but also there's alterations to the flow side of the balance as well. As you could see in the gray shows the distribution, the historical distribution of flows at the Sioux City and Herman, and the blue shows the the current distribution of flows at those two sites. So there's been an alteration in the magnitude, the frequency, the rate of change, the timing, and the duration of flows. And this has also affected the amount of stream power and the amount of sediment that's being transported. So next I'm going to talk about the USGS sediment sampling program. The objective of this program is to collect a sediment sample that's representative of the conditions at the time. And that poses a challenge because sediment concentrations can vary anywhere from 500 to 1,000 feet, or 1,000% from one side of the river to another side, or from top to bottom, and certainly with time. The USGS collects about 12 to 36 samples per year at these 6 sites. And how they do that is to collect an equal discharge increment sample. And what that means is they make a discharge measurement. They divide the river into equal increments based on that discharge measurement, and then take the center of each of those increments and take a depth integrated sample throughout the water column. Then that sample is analyzed for concentration, it's analyzed for particle size, and periodically they'll also collect some bed material samples as well. But more and more, the USGS is working with surrogates and technological advances in order to further obtain more accurate sediment data. One of the primary surrogates that we use is turbidity. Turbidity measures an optical property of the water, the backscatter from the sediment particles in the water. And that we measure continuously at a site. And then we have those 12 to 36 samples that we measure, the physical samples. So that might be once a month we would go out and collect one of those samples. Well, in between that time, we're collecting the continuous turbidity, and we can relate that turbidity to that physical sample when we collect it, and then develop a relation with that between turbidity and the concentration, and then use that relation to back calculate or back estimate what the concentration would be during those periods when we're not out there taking the sample. So we could obtain an hourly or daily or much finer increment estimate of the concentration. Similarly, we use the acoustic velocity meter to do the same thing, but that uses a sound wave throughout the water column, and then based on the return characteristics of that sound wave, we can say something about not only the velocity of the water, but also the concentration of sediment in the water. Another device that we use is the LIST. This is a laser diffraction system. So it uses a laser light in order to determine which passes through a water sample that's pumped up from the river. And so we can look at in real time what the concentration of the sediment is in the water. And in addition to that, we can use how that laser bends around a particle or diffracts to estimate the particle size as well in real time. So here's a compilation. The Corps started their sampling in 1936, the sampling program, and the USGS took over in 76. And so here's a compilation of the concentrations at 2 sites, Omaha and Heimann, to show what's happened with sediment concentration in the Missouri over time. And I include this 1952 to 67 window here. That's the period under which the impoundments were constructed. I don't mean to imply that that's the single factor that's causing this decline, but it's certainly one of the factors. And you can see the dramatic decline at both Omaha and Heimann that's occurred with time. But another factor is not only is sediment concentration declining on the main stem, it's declining on several of the major tributaries as well, including the Boyer River shown here and the Nishnabotna River. So there's a number of things going on. What this map shows is the current suspended sediment loads compared to the pre-1953 loads at selected stations. So here at Yankton, the current sediment load is about 1% of the pre-1953 sediment load at that station. At Kansas City and Hermann, it's about 22% of the pre-1953 load. And then at Tarbert Landing on the Mississippi, it's about 28% of the pre-1953 load. The reason it's a little greater as you move downstream is because you have tributaries that are that haven't been affected that contribute to it and buffer some of the effects of the impoundment upstream. Tarbert Landing and the Mississippi are important, or sediment is important at those locations as well in terms of the delta and the buildup of wetlands and the ecosystems that rely on that sediment being deposited there as well. So the next topic is going to be a study that was conducted by the U.S. Geological Survey in cooperation with the U.S. Army Corps of Engineers, Kansas City and Omaha districts to look at a generalized sediment budget for the lower Missouri River. The impetus for this study was a 2011 report by the National Research Council, and in which they state that the Corps and the USGS should develop a detailed Missouri River budget from the headwaters to the river's mouth, with provisions for revisions and updates as new data become available. So what this study was basically a first step towards that goal. We used existing information and to establish the initial framework for a budget for the lower Missouri River and for that post-impoundment period, for that post-1968 period. And then when and where possible, we incorporated bedload into that budget. So this schematic shows a representation of that budget. So the control volume or river reach is defined by the upstream station and the downstream station. The gains include tributaries or bank erosion or floodplain erosion, and the losses include bed deposition or floodplain deposition within the reach. So then it becomes an accounting principle or accounting exercise where you take the inputs minus the outputs and you come up with some residual value. If that residual value is about 0, that means that your inputs and your outputs are about equal, so that reaches an equilibrium. If that residual is less than 0, then you have a degrading condition. If that residual is greater than 0, you have an upgrading condition in that reach. So why is this important? Well, it's certainly important in terms of the placement, the design, the maintenance, the creation of this shallow water habitat, the emergent habitat along the river. It's also important in terms of the maintenance, design, implementation of various types of infrastructure, whether it be municipal infrastructure or industrial or transportation-related infrastructure along the river that relies on a nice, stable channel bed with time. This busy graph shows the availability of the sediment at the stations that I used to develop the budget. And what I wanted to show was ideally we would have solid lines. This is at 1968 start time and through 2014. Ideally, all of these would be solid in order to develop the budget, but there were 6 sites that we had complete record, and there were 22 stations for which we had less than 22% of the record. And I can appreciate what went into collecting what of record is available, so I don't want to discount what we do have, but it does make a challenge in order to develop a budget when you're missing a lot of the information, but you just do the best with what you have. In terms of this bedload availability, there's even less information. There's a few discrete samples at some of the upstream Missouri River stations, but most of this information at the other Missouri River stations is the dots represent theoretical values. So this is based on on an equation to estimate what the bed load is. And there's no information at all available at the tributaries, unfortunately. Something that I thought might be of value is to show what the relative contributions of total suspended sediment are for the Missouri River. And this is for that 1975 to 1991 period, which seems like a kind of an odd period, but that just happened to be the period for which we had all the record available in order to compare the various stations. So I'll go through the top 5 contributors of sediment to the Missouri for that period. Number 5 is the Nishnabotna River in Iowa at 6.7 million tons per year. The Kansas River is number 4 at 9.6 million tons per year. The Grand River was number 3 at 11.7 million tons per year. And the Platte River in Nebraska was number 2 at about 13.2 million tons per year. And the number 1 contributor during that time was the Yellowstone River at about 13.7 million tons per year. So 4 out of the 5 top contributors are downstream of the impoundments. And those top 3, the Yellowstone, the Grand, the Platte River, those from year to year, that order can vary. The Grand could be the top contributor one year, and the Platte might be another year. So let's go through an example budget exercise then. And this is for the Yankton to Sioux City reach. And for that, again, for that 1968 to 2014 period. So the first step is to find out our inputs, and that's up at Yankton, just downstream of Gavins Point Dam. So that was about 330,000 tons per year. We add the gains from the tributaries, the James River, the Vermilion, and the Big Sioux. That's about 1 million tons per year on average during that period. The losses, that's not something that we normally are going to collect. That the deposition on floodplains or the deposition in the channel, so that's an unknown. The output from the reach was about 11.2 million tons at Sioux City. So if you add up the inputs and gains and subtract the losses and outputs, you get a negative residual of about 9.8 million tons per year. So that means that Yankton and the tributaries don't nearly match the sediment load at Sioux City. So what that means, first of all, is that we have a degrading condition. What that also means is that it's got to be coming from somewhere, and it's coming from the channel bed and the channel banks. And that's evidenced by the fact that the downstream of Gavins Point, the riverbed has dropped about 7 feet between 1968 and 2012. Briefly looking at another reach, this is the Omaha to Nebraska City. In this case, it's about a negative 500,000 tons, or it's about 1.7% of that Nebraska City load is what that residual, and looking at the, again, that's the inputs minus the outputs, and that difference represents about 1.7%. For all practical purposes, that's equilibrium because we couldn't measure it within about 10%. So anything less than about 10% is going to be, should represent an equilibrium condition. What I wanted to show with this is that was for the entire period. But if you look at that residual from year to year, which we can do at this site because we happen to have all the inputs and outputs on an annual basis, on a year to year, well, over long term, it might be about 1.7%. But from year to year, it varies from anywhere between negative 25 to 40%. So it's showing that on a finer increment, you have much greater variability in sediment transport. And sediment doesn't transport nice and evenly, it transports episodically, and depending on flow and other conditions. Another factor that we accounted for but weren't really able to incorporate into a budget that was dominated by suspended sediment is dredging. We know what the annual amounts are, and we can divide that up by reach, but again, it's difficult to try and incorporate that directly into an input or an output when the rest of your budget is focused on the suspended load. There's a high correlation, though, between dredging and bed degradation. Dredging takes place primarily in the urban areas like Kansas City area, St. Joe, Columbia area, and there's a high correlation with that and bed degradation. So dredging's under a lot of scrutiny and by the Corps and other entities in order to ensure that the amounts that's being dredged is in line with what the bed degradation that's taking place, and that relation is stable and doesn't result in degradation conditions that result in too much damage to infrastructure, etc. So when you conduct this type of exercise, it's useful to know what you do know, but it's also useful to know what you don't know. And there are a number of things that represent data gaps, including the bed load and that bank erosion and storage and floodplain erosion and storage, which we know can be quite sizable based on the aftermath of the 2011 flood. One tool that looks promising in terms of measuring bed load on the Missouri River are these multibeam surveys that Carrie Elliott talked about last month in her talk. And this is a map of the Missouri River bottom showing the dune patterns and the various features. And if you take these and have a time-lagged set of these maps, so you go out and you survey, you go out and then in an hour collect another survey, and then an hour collect another survey, then you compare those maps of the channel bottom, then you can start seeing where the erosion and deposition is taking place. And then based on that erosion and deposition, you have some idea of the bed movement that takes place. And from that, we can obtain an estimate of the bed load transport. So that's something that's being developed by the Corps of Engineers and tested by the USGS as well. Last topic that I'd like to discuss is this idea of a natural sediment regime. River management tends to focus much more on stream flow than it does on sediment, and the Missouri is no exception. One way that I'd like to illustrate this is by showing the number of stream flow stations throughout Missouri, which is about 270, and which will drop to about 220 after July 1st because of budget cuts. But and then we have about 10 sediment stations. And so this shows that disparity in stream flow versus sediment, and these stations are customer driven. This is what the state, local, federal agencies are asking USGS to collect in order to make decisions and manage their resources. And so what the customers are telling us is they want stream flow. They're not really interested in sediment. This was a quote that I thought was pertinent. It states that the natural function of rivers is to carry the sediment and dissolve solids to the ocean. Humans interfere with this function as they utilize the water resources of the earth, often without realizing that the water is already committed by nature as a carrier of sediments to their ultimate destination. And when Dr. Ponce refers to utilize, in my mind, that could be withdrawals, it could be impoundments, it could be augmentation of flows through urbanization and additional runoff. So if streams have a job to do, and that job is to carry sediment, is sediment a stream pollutant, or is it a job well done? Well, obviously it could be both, depending on the circumstances. But if you Google sediment and streams, chances are you'll see quotes such as this, that sediment is the primary factor in the deterioration of surface water quality, or that in terms of pollution area issues, sedimentation is going to be near the top. or in a publication that states that once sediment has been delivered to the valleys and the channel, it becomes a fluvial problem. Well, it becomes a fluvial problem if the system is out of balance, if those driving forces and resistant forces are out of balance in that particular system. And there are many contributing factors to cause that. Another quote states that to many environmental scientists, all sediment is treated as a pollutant. This perspective is in conflict with the need to introduce sediment to sediment-starved reaches below impoundments, and the Missouri River would certainly fall into that category of having sediment-starved reaches, as we saw from the Yankton to Sioux City reach. So in those such cases, sediment wouldn't be a pollutant. It would be welcome in order to augment the loss of the sediment that's being transported because of the impoundments in that particular reach. In terms of stream restoration, there's quite a gambit, and it runs anywhere from full restoration, which is to bring the system back to a pre-settlement condition and restore it to its original state. On the other end of the spectrum would be a condition where you alter a system and then you leave it alone and let it do what it's going to do. Somewhere in the middle is the approach I think is what's attempted to be applied to the Missouri River, and that's stream naturalization. And naturalization aims to establish morphologically and hydraulically varied yet dynamically stable channels that are capable of supporting biologically diverse aquatic ecosystems. And through the establishment of the emergent habitat and the shallow water habitat, I think that's what the goal is towards this stream naturalization approach. So the target then is to obtain a balance between the sediment supply and the transport capacity. We may not be able to get back to some historical condition, nor do some want to get back to some historical condition, but we can make the present condition be one that has a stable channel, one that is diverse and provides habitat for a variety of aquatic communities. So in summary, I'd like to go back through those 4 topics and provide a takeaway message. In terms of the historical perspective, there's been substantial changes to the historical instantaneous mean sediment concentration, and that is in response to several alterations to the Missouri River channel, including the flow regime as well. The current sediment sampling program by the U.S. Geological Survey is conducted at 6 main stem stations, along with numerous tributaries along the Missouri, and we sample for concentration and particle size and bed material as well. In terms of the generalized sediment budget, this is a tool to help determine if a sediment balanced system exists over various spatial or temporal scales, and the relative sources and storage of sediment within that system or that reach. In terms of a natural sediment regime, even in an altered stream such as the Missouri, it's still possible to obtain a naturalized flow and sediment regime, one with flow and sediment transport that's in balance, a channel that's stable, and a dynamic system that provides a diversity of habitat. And with that, I'd be happy to try and answer any questions you might have.
you.